Alright, today we're going to be talking about section 10.4, which is about random variables and probability models. We'll get up about through half the lesson today and half the lesson in our next video. We'll just get some definitions out of the way here. A random variable assumes numerical values as a result of some event. We denote random variables by capital letters such as capital X, and the values they can assume by subscripted lowercase letters such as x1, x2, x sub 3, so on and so forth. So for example, if we let the roll of a die be our random variable, then R, capital R, can have the values 1 through 6. We could also use the word outcomes to describe the values that it could take on. Those are the 6 outcomes that you could have when you roll a die. So we've talked about this sort of stuff before. We've even had probability models before. We're just giving this the name a random variable. Like I said, we talked about probability models in section 10.1. This is a review of that. Here we have a probability model for the rolling of a die. So you could have these outcomes 1 through 6 with these given probabilities. Notice the capital X, because that is our, well, they used X, I used R earlier on here, but you could use either. And then the probability of X is 1/6. It's the same for each of the 6 outcomes. We're going to talk about the expected value. So on your notes below this example, it starts going into expected value. You have this blue box on your notes that gives the definition of expected value. A lot of notation here that looks very complicated. Basically, the expected value is the weighted mean given the outcome and the probability in the random variable event. So this symbol here, mu, it's read as mu, is just a notation for mean. So the expected value is just the average value that you would expect to get. So the expected value for our rolling of a die, you can put this right under that probability model that we were looking at before. Expected value for the rolling of a die, or E of X, is going to be found by taking each of those outcomes and multiplying it by the probability that it occurs. So for each of them, it's 1/6. So we're going to take 1 times 1/6 plus 2 times 1/6 plus 3 times, so on and so forth until you get to 6 times 1/6. That would be the same thing as just adding up those values 1 through 6 and then dividing by 6. So the expected value when you roll a die is going to be, I believe this is 21 divided by 6, which is 3.5. So obviously you can't roll a half when you roll a die, but that is still the expected value that you would get when you roll a die, is to get 3.5. All right, example 1 talks about a loaded die. It says a die is loaded to favor faces 5 and 6 as shown in the probability model below. So we're still talking about rolling a die, but now if you notice, the probability of getting a 5 or a 6 is not the same as the other 4 outcomes. Getting a 5 has a probability of 1/5, and getting a 6 has a probability of 2/5 or 0.4. So our expected model here, excuse me, our expected value here, E of X, we're going to find in the same way where we take those outcomes and we multiply them by the probability of each happening. So 1 times 0.1 plus 2 times 0.1 plus 3 times 0.1, so on and so forth. And we end up with 4.4. So it says, if this die were tossed repeatedly, we expect the long-term average to be 4.4. This particular die. We said with a normal die that has a 1/6 chance of getting any of the outcomes 1 through 6. Earlier we said that that would be expected value of 3.5. So this one, because the 5 and 6 are weighted a little bit heavier, the expected value is higher. It's 4.4. You could do this in your calculator using the frequency list like we had done previously in the last section, 10.3, when we did the quiz scores given a certain frequency, and we came up with the one variable stats, the 5-number summary. We used a frequency list. We could do the same thing here, where we made the outcomes L1 and the frequency with which they occur, which is the probability, our list 2, and then make that our frequency list. That'd be another way to handle this problem. You could use your calculator, use L1, L2, and then do one variable stats, and your X bar would be your expected value in your one variable stats. So that'd be another way to do this. With a list this small, it's probably just as fast to do it by hand. In example 2, the raffle example, it says, as a fundraiser, a student group sells 500 raffle tickets at $2 each. And at the drawing, the top prize will be a gift certificate for $100. The second prize will be a $50 gift certificate, and there will be 5 third prizes, each $20 gift certificates. So what I started putting together here is the probability model here. So I have my random variable X, which is going to end up being the gross winnings, and I have that right here, that X is gross winnings. And kind of above this probability model here, just to organize what I was doing here, I wrote what these things actually represent. You have your first, your prizes here, your first prize, second prize, third prize, and then people who don't win prizes, we'll just throw them in that category at the end called the losers. But our X is the gross winnings that we're going to get given each of these cases. So if you are going to win first place, that means that you've won $100, but you've paid $2 for that raffle ticket. So we're saying that each person's bought one raffle ticket. So your gross winnings are going to be just $98. That happens with a probability of 1 out of 500. There's going to be one first place winner out of the 500 raffle tickets that are sold. Your second prize is a $50 gift certificate, so your gross winnings after paying $2 for your raffle ticket is going to be $48. And that happens with a probability of 1 out of 500. There's one second prize. There's going to be 5 third prizes, so 5 out of the 500 are going to win a $20 gift certificate, which means your gross winning is $18. And then if you don't win anything, your gross winnings is actually negative, the $2 that you paid in, so -2, and that's going to be everyone else. So we have 7 people here that win, which means that 493 are not going to win. So our expected value, we're just going to, again, you can use your frequency list or your one variable stats and call this L1 and this L2 on your calculator and make L2 your frequency. Or with, again, with values or this few number of outcomes, you can just calculate this by hand by multiplying each of the outcomes by their probability. Our expected value ends up being -1.5. For the expected value, and I already have this up here, the expected value being -1.5 tells us that on average people lose $1.50 playing this game, which makes sense because most people don't win anything. You only have 7 prizes where we actually win money, and the probability of winning is pretty small. So on average, people lose $1.50 playing this game. All right. Our next example is again using a probability model. Our random variable this time is going to be given to us through this lucky ace discount at a golf course. It says, when a player signs in at this golf course, the manager shuffles the 4 aces and lays them down face down in the counter. And the player will turn 1 card over. If it's the ace of diamonds, the player gets to golf for free, which is saving them the $50 fee to golf. If it's the ace of hearts, the player gets to turn over another card. And if the second card is the ace of diamonds, the round of golf is half price. If either the first or second card is one of the black aces, the player gets a $10 discount. We want to know what the expected cost of a round of golf is here. So to start with, we're going to find the probabilities of each outcome. We have D is going to be diamonds, H is going to be hearts, and B is going to be black. And I also have over here to the side, we're going to use some of our probability notation and find those probabilities over here. So the probability of a diamond is going to be 1/4. Okay, there's 4 aces. The probability of getting the ace of diamonds is 1/4. The probability of getting a heart and then a diamond, well, the probability of getting a heart is 1/4. And then getting the diamond, well, remember, you've already turned over that one card that was a heart. So the probability of getting a diamond then would be, with the 3 cards left, 1 out of the 3. So the probability of a heart and then a diamond is just going to be 1/12. The probability of getting a heart and then a black ace, well, the probability of getting a heart again is 1/4. And then the probability of getting a black ace of the remaining 3 cards, if you already pulled a heart, the remaining 3 aces that are face down, 2 of them are black. So you have a probability of 2/3 of then getting a black if you already got a heart. So I'm not showing all the notation here, but we're actually doing conditional probabilities. 1/4 times 2/3 is 2/12, and I'm leaving everything just in terms of twelfths right now. Actually, I didn't leave this one in terms of twelfths. We could call this 3/12, just so we have kind of an idea of how they compare. Now, the probability of getting a black. If you look at everything else that happens here, all of these probabilities together, the 3/12, the 1/12, and the 2/12, all 3 of those together will add up to 3 plus 1 is 4 plus 2 is 6. That adds up to 6/12. That means that the only other thing that could happen happens with a probability of 1/2 as well. Because these 3 things that we did first are the only other thing that could happen besides getting a black ace first. You could get a diamond, and then if you get a diamond, it told us if you get the ace of diamonds, then the player golfs for free. So if you get a diamond, that's one thing that could happen. But if you get a heart, then you could either get a diamond and then a black. So those are 2 other things that could happen. The only other thing that could happen in this scenario is that you get a black ace first. So that happens with a probability of 1/2 because the other 3 add up to 1/2, and these are complements. So we can start filling in our probability model down here below. We have my outcome here I have is x equals cost, so my random variable is the cost. Then I have the, how the cost relates to these different outcomes. If I have a diamond, my cost is going to be $0. I get to golf for free if I flip over that diamond first. If I get a heart and then a diamond, I said that my round of golf is half price, so it's $25. I could get a heart and then a black card, which means I'm paying $40. That would be this $10 discount that it says right here. And then it says, oh no, I'm sorry, that's not the right one. Oh, it says if it's the ace of hearts, the player gets turned over to, yeah, it was that scenario. So that was $40 there. So if it's either of the blacks, or if they get a black to start with, then you have your $40, your $10 discount. All right, so the probability of these things happening, we found over on the side there. We have 3/12 or 1/4, 1/12, 1/6, or the 2/12 that's over there on the right, and then the 1/2. So our expected value, if we multiply each of these times their, let me start by doing this, expected value, which is going to be each of these times their probability. 0 times 1/4 is obviously 0, and then 25 times 1/12 and so on and so forth, what we end up with is 28.75. So our expected cost for a round of golf is $28.75 when we are taking a part in this lucky ace discount at this golf course. So those are a couple of examples involving probability models and random variables and expected value. So basically, what it comes down to is probability model helps us to organize the outcomes and the probabilities. The expected value is each of those outcomes multiplied by their respective probability, and then we add those together to find out what the expected value is. In our next video that'll finish up this section, we are going to talk about binomial probabilities.